Hello and welcome to this month's webinar from the IEA Clean Coal Centre. My name is Debo Adams and I'm Communications Manager here. Our webinars are based on our technical reports which are available to download from our website www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after a one-off registration. Please visit the website for details. Today's webinar is on high-temperature steels in pulverised coal technology and is presented by my colleague Carl Nicol. The report is out in draft at the moment and will be published and available on our website in a couple of months. If you have any questions during the presentation, please use the Ask a Question box at the top of your screen. Add your email address as well so that Carl can send you a fuller answer if we run out of time. Okay, Kyle, over to you.
Thank you, Debo. My name is Carl Nicol and I'm about to present the red-hot topic of steels in coal-fired power plant. Here's the contents page. Moving on. First of all, increasing the maximum steam temperature in pulverised coal-fired power plant increases electrical efficiency. Higher steam temperatures can be achieved with stronger steels. However, the maximum steam temperature is limited by materials that can operate in high temperature conditions for service lifetimes of up to 40 years without failure. New materials are qualified for over 10 years in numerous mechanical and chemical tests, and then models project the long-term performance in service. These projections can be wrong, and some steels in long-term service have encountered unforeseen problems. This is why some metallurgists say that materials cannot be properly qualified until the end of their service lifetime, which can be up to 40 years. Supercritical and ultra-supercritical pulverised coal technology have a significant amount of operating experience. This presentation will review the problems and solutions found with high-temperature steels and research efforts to improve such steels. This slide summarises the damage mechanisms involved on high-temperature steels in coal-fired power plant. Broadly speaking, there's two types. There's chemical attack, which can be divided into fireside corrosion, which is inside the boiler, and then steam side oxidation, which is inside the steam loop components. Both of these chemical attack mechanisms slowly degrade the materials. There's also constant stress, which is caused by high pressures and high physical loads. This results in cracks on the inside of the material, and this is known as creep damage. There's also cyclic stresses, which is induced by fluctuating temperatures and pressures. This results in cracks on the outside of materials, and this is called fatigue damage. So, steels are made up of loads of tiny crystals in the nanometer scale. These steels can be strengthened with three main techniques. The first is solid solution strengthening, which is where small amounts of different sized alloying elements are diffused into the metal to prevent movement. The second is dislocation strengthening. This is where the material is deformed plastically at low temperature. This tangles the crystals in the material, which prolongs crystal life. And finally, there is precipitation strengthening. This is where the amount of alloying with at least two other elements is increased so that they create a second phase known as precipitates. These precipitates prevent the movement and recovery of crystals. This table lists the materials used for high temperature boiler components in supercritical and ultra-supercritical power plant, with the resistance required to the four main damage mechanisms and other comments. All temperatures mentioned in this table and throughout the webinar and in the report are that of the steam, not of the metal or the flame, which exceed that of the steam. This is the same table for the steam turbine component. I'm not expecting you to remember these tables. I've put them here purely to demonstrate the complexity involved in power plant materials. They are in the report for analysis. So, ferritic steels, they have a low amount of alloying and are strengthened with solid solution strengthening and dislocation strengthening. Ferritic steels are easy to manufacture and they have a good performance all round up to 565 degrees Celsius, where they are then limited by steam side oxidation. They are the only steel that does not require expensive and time-consuming post-weld heat treatment. Ferritic steels made up most of the components in subcritical pulverised coal-fired power plant, and the chrome alloy ferritic steels such as T22 are used in water walls and other low-temperature applications in supercritical pulverised coal-fired power plant. The installation of low-NOx burners in boilers has caused excessive corrosion of ferritic steels near the burners due to differences in combustion stoichiometry. This problem has been solved with protective high chromium weld overlays. T24 is a new ferritic steel developed in Europe for ultra-supercritical power plant. Shortly after first commissioning in 2010, multiple cracks developed in T24. Evaluation found the cracking mechanism to be stress corrosion cracking. Preventative measures such as additional heat treatment during the welding procedure, adjusted water chemistry, adaptive chemical cleaning process and startup procedure were introduced in 2011, and to date no stress corrosion cracking has been detected. Martensitic seals allowed progression to supercritical steam conditions. High alloying of chromium, molybdenum, nitrogen, niobium, vanadium, and others achieve a significant amount of precipitation strengthening. Generally, the 9 to 12% chromium martensitic steels have high creep and fatigue resistance, a low coefficient of thermal expansion, a high thermal conductivity, and good fabricability. 9 to 12% chromium martensitic steels can operate up to 600 degrees Celsius at high pressures of up to 25 megapascals, but they are limited by the resistance to steam side oxidation. 11 to 12% chromium martensitic steels can operate up to 620 degrees Celsius at low pressures of less than 10 megapascals, but are limited by their strength. Martensitic steels do, however, require expensive and time-consuming post-weld heat treatment. They suffer from long-term weakening mechanisms and they are susceptible to cracking. So, one of these cracking mechanisms is type 4 cracking. Type 4 cracking occurs in the weld. Type 4 it's called type 4 purely because there's 4 types, as displayed in the top right-hand image. Type 4 cracking of P91 has been significant in the UK and Germany, with failures occurring within 2 years or 10% of projected service life. Evaluation has shown the cause to be insufficient alloying or incorrect temperature profiles during the fabrication of the parent material, or insufficient alloying or incorrect temperature profiles of the weld material and the heat treatment procedures during the welding procedure. New components have reduced the risk of type 4 cracking through component design, which minimises stress in the weld, and so that the welding procedure and post-weld heat treatment procedures are easier to carry out correctly. And Also, it has to be ensured that the parent material has the correct amount of alloying and is fabricated correctly. So Martensitic steels suffer from long-term weakening mechanisms. With all chromium Martensitic steels with 9 to 12% chromium, the tungsten and molybdenum will precipitate out as large and coarse Laves phase, which consume all the small strengthening precipitates. Due to lava phase weakening, P92 has been found to have long-term creep strength not much greater than P91. Higher chromium Martensitic steels with 11 to 12% chromium have an accelerated drop in long-term creep resistance, which is more than what can be explained by Laves phase alone. The increased chromium levels cause precipitation of coarse nitrides known as Z phase. So the combination of Laves phase and Z phase means that higher chromium Martensitic steels are weaker than lower chromium Martensitic steels. Cyclic operation has resulted in higher fatigue damage of high temperature components, but also creep fatigue damage. Creep fatigue damage is where creep damage and fatigue damage interact synergistically, which can result in failure sooner than either creep or fatigue damage alone. Creep fatigue damage has been a significant cause of failures in T91. It is important to note that not all material codes currently assess creep fatigue damage. Austenitic steels are used in superheaters and reheaters of ultra-supercritical power plant. They're seen every day as stainless steels. High alloying with elements such as chromium and nickel achieve high solid solution strengthening and high precipitation strengthening. They have excellent performance all around 665 degrees Celsius, but they have a high coefficient of thermal expansion, which results in cracking when used in thick section components. Austenitic steels are therefore limited to thin section components. Dissimilar metal welds are welds between different types of materials. There is a high risk of cracking at dissimilar metal welds due to differences in material properties. One is the different carbon concentrations cause carbon to diffuse from areas of high to low concentrations, which alter the material properties such that the strength decreases. They expand at different rates, and also localized oxidation forms, which is an ideal place for crack initiation. So, cyclic operation of older plants results in failure of dissimilar metal welds. New components have reduced the risk of dissimilar metal weld cracks through thermal coefficient matching and component design to minimize the stress on the weld. Excessive slagging and fouling will increase creep damage as well as reduce boiler performance. Soot blowers use compressed air, steam or water to knock off deposits. New intelligent soot blowers are retractable, can vary the injection pressure and use heat transfers to determine when cleaning is required. This combination allows for maximum cleaning, minimum resource usage and minimum material damage. Typical payback periods for some plant can be less than 1 year, and also this online cleaning technique can eliminate the need for offline boiler cleaning for up to 20 years. An unforeseen advantage of cyclic operation is the fact that cold starts expand boiler tubes by up to half a metre. This can effectively dislodge the deposits, which again reduces the need for offline cleaning. Feed water for the steam cycle can be treated in two main ways. Firstly, deoxygenated feed water, and secondly, oxygenated feed water. Deoxygenated feed water results in no steam side oxidation, but the treatment method can dissolve iron in some situations. This is known as flow accelerated corrosion and causes a thinning of the pipes. Flow accelerated corrosion has resulted in numerous failures and fatalities historically. Despite this, deoxygenated feed water is still used in over 70% of fossil fuel power plant today. The alternative is oxygenated feed water treatment, where this creates a protective oxide layer on the inside of the material surface to prevent it from further steam side oxidation and flow accelerated corrosion. Another way to protect against flow accelerated corrosion is with the use of higher chromium ferritic steels. If pulverised coal-fired power plant are cycled beyond their design specification, then there is a high chance of failure, such as type 4 cracking or dissimilar metal weld cracking. This figure shows the relative lifetime decrease for high temperature components with the introduction of cyclic operation. It can be economically favourable to repair or replace components before failure, which could lead to catastrophic failure. To do this, the steel lifetime accounting for cyclic operation is required. This corrected steel lifetime can be accurately measured with modern software packages and material examination tools. This technique is known as condition monitoring. Preventative maintenance strategies integrate information from process measurements and condition monitoring, online and offline, for multiple components and consolidates them into a single computer program. This is known as a computerized maintenance management system, or CMMS. This can give a quick overview of the entire plant condition, providing risk and cost information in order to make a proactive and economically favourable decision. One utility in the USA established CMMS across its 27 oil and gas-fired units. The results were 30% fewer forced outages, a 7% increase in peak reliability, and maintenance costs reduced within a few months. The orange bars illustrate the highest steam temperatures achievable for commercial steels in major steam cycle components in modern ultra-supercritical plants. If steels can be developed for thick section components at 650 degrees Celsius, as shown by the purple bars, then ultra-supercritical power plant could operate at 650 superheat and 650 reheat temperatures, with a rise in net electrical efficiency of roughly 1 to 3% depending. Additionally, stronger steels have thinner component walls. Thinner component walls are less sensitive to fatigue damage, which makes them more suitable for cyclic operation. Improving the long-term creep resistance of high chromium Martensitic steels, such as 12% chromium Martensitic steels, is a promising route for developing a 650 degrees Celsius steel, as they have inherently higher resistance to seam side oxidation due to the higher chromium levels. An interesting strengthening concept is to promote the formation of small Laves phase and Z phase precipitations during the fabrication of the parent material, thus turning the weakening mechanism found in existing Martensitic steels into a strengthening mechanism. Another interesting concept is sub-grain strengthening. This is where the precipitation itself is strengthened. Short-term results from projects in Japan and Europe have shown that sub-grain strengthened 12% chromium Martensitic steels are stronger than that of commercial state-of-the-art P92 by up to 55%. New AFA Austenitic steels have a low thermal coefficient of thermal expansion, which would allow them to be used in thick section components. They are being developed for use at 660 degrees Celsius. And also, coatings for Martensitic steels are in development. This would allow the use of existing, cheaper parent materials which are coated to use them at higher temperatures. Coatings are yet to prove effective, and boiler manufacturers have historically avoided them. So to conclude, ferritic steels are well proven and seem to have reached their limits. Martensitic steels are heavily used, problems have been found and solutions have been developed. Austenitic steels have performed well, but they are limited to thin section applications. Operating power plant beyond their design criteria, such as severe cyclic operation, could result in failure, which could be catastrophic failure. Consequently, new methods can accurately estimate when failures may occur, so preventative action can be taken to minimise financial losses. 650 steels could be commercially available in the late 2020s for net electrical efficiencies reaching 50% on an LHV basis in some cases. Whilst I'm on the subject of high temperature materials, the next IEA Clean Coal Centre workshop on advanced ultra-supercritical coal-fired power plant, which is where nickel alloys is used in the highest temperature sections to reach 700 degrees Celsius maximum temperature, will be on the 14th and 15th of October this year, hosted by CSM in Rome. The workshop will consist of 1.5 days of presentations and a half day site visit of the CSM facilities, and also there will be a conference dinner in Rome. This workshop will bring together international experts to assess the present state of AUSC technology and provide a valuable networking opportunity. The first workshop was held in September 2012 and was hosted by EVN in Vienna. The countries highlighted in red on this map show where the 77 attendees of this workshop are from. There were 26 oral presentations and 4 poster presentations. The workshop was well received, and it was decided to hold the workshop every 2 years due to the nature of materials development. I'd like to end the presentation there. If you could rate this webinar at the top of your screen, that would be greatly appreciated, and I welcome any questions.
Thank you, Kyle, for a very interesting presentation. Can I just remind you that Kyle's PowerPoint will be available to download from the webinar page of our website later on today. Now I'm just going to see if any questions have come in for Kyle. Here we go. First one, Kyle. Has your report covered nickel alloys?
Thank you for asking that question. This report hasn't covered nickel alloys. However, my last report entirely covered nickel alloys. I've also done a webinar on nickel alloys. This is under the title of Status of Advanced Ultra-Supercritical Coal-Fired Power Plant.
Thank you. And of course, Kyle's previous report is also available from our website. Kyle, do you think 650 degrees C steels will become commercial?
Eventually. The question is when they'll become commercial. One research group states that it'll have the ingredients ready for a 650 steel by 2017. A decade of testing will be needed to qualify the material, and then the fabrication methods and supply chain would have to be established. So in the 2020s, hopefully mid-2020s, late 2020s, we can have a commercial 650 steel.
Kyle, do you know of any plants that have experienced T23 material weld failure?
I've not seen that in the literature, but I have heard of it at a conference. So no. T24, yes, but not T23.
Okay, Kyle, another question has come in for you. The ASME has cautioned about the use of P92 recently. What is your position on the use of P92?
Well, as explained in the webinar, the P92 suffers from Laves phase weakening, and stringent post-weld heat treatment has to be used along with stringent alloying composition. Personally, I would use P91. This is a well-established material. I know it's not as strong, but it's easier to use and it's well proven.
Thank you very much, Kyle. Well, that seems to be the end of the questions for now. If you have any more, do email Kyle and he'll reply to you, I'm sure. Next month's webinar will take place on Wednesday, what date is it? It's 16th of April, midday UK time, and the details will be announced soon. Thank you very much for listening. Goodbye.